Okay, so this, when we get this all down to that, if we were talking about variable specific heats, we still have to worry about variable and constant specific heat. We can say that the change in internal energy bar total, which means the change of internal energy on a molar basis, is equal to the summation from I is equal to 1 to J of Yi times U2 bar minus U1 bar of each component, which makes sense. If it was 100%, we've done that before, it's just U2 minus U1. That's all the problems we've done in chapter 6 and everything like that. And now we're saying, no, not all of the internal energy change is going to come from this one substance. There's going to be multiple substances that are going to provide this. We're going to look these up in the tables and figure out what this is. Or we can say that the change in internal energy total on a mass basis is going to be equal to the summation of I is equal to 1 to J of the mass fraction of each component times U2 minus U1 of I. Now, one thing you should know here is air. Air, we're given values, U2 minus U1, we're given those values in our tables on a mass basis. Carbon dioxide, carbon monoxide, oxygen, nitrogen, we're given those on a molar basis. So that might lead you down which path you want to go down here. Okay? Or, we could also say, we could say this is equal to, I'm going to say here, I would say, or, this is equal to the summation the mass fraction of each component times U2 bar minus U1 bar all over the molecular weight of the component. Okay, right now, this over the molecular weight, this changes this U2 minus U1 into a mass basis, and then we take it times the mass fraction. Okay, that also works. Nothing wrong with that. Same. Okay, same goes for delta S. Same thing goes for delta U. But remember, with entropy, remember that delta S of each component, I gotta make sure I get mine over here. Delta S of each component is equal to, let's do it this way, S2 bar minus S1 bar of each component, which is going to be equal to S2I degree bar minus S1I degree bar minus R bar, natural log of P2 all over P1. We have to remember this is what we have here. We have to remember we have absolute entropies, the S degree that we have to deal with. Okay? Now, what are these here? And I should say should be Pi2 and Pi1. What is happening over here? These are partial pressures. These are partial pressures because of the pressure of the component. Okay? But here I need you to pay attention. If you have been just sitting around listening to me because I calm you down and you look forward to the second lecture on every day because it's just wonderful to see me in my room talking to my webcam with my Thomas the Tank Engine trains and whatever the ridiculous stuff is up here. I think this is a origami paper snowflake and a crown, and then there's a pencil box down here that looks kind of like Dwight Schrute. And I haven't closed all my windows blinds. Here's where I need you to pay attention. Okay? Because this, if you are a mixture in state 1 or state 2. State 1 and state 2. So what I mean is you have a mixture of nitrogen and oxygen in state 1, and you have a mixture of nitrogen and oxygen in state 2. Mixture in state 1, mixture in state 2. Mixture doesn't change. Mixture doesn't change in state 1 and state 2. It's the same thing. We're not working with that. What happens here is the partial pressure at state 2 over the partial pressure at state 1 is going to be equal to, look, the mole fraction at state 2 times the total pressure at state 2 over the mole fraction at state 1 times the total pressure at state 1. And notice that since you're mixed in state 1 and you're mixed in state 2, we know that the mole fraction at state 2 is equal to the mole fraction at state 1. We know that that's the case. There's nothing wrong with that. And so this is going to cancel, and we're just going to get P2 over P1. So if, and this is very, very important, if you're a mixture in state 2 or state 1, it doesn't matter. You can put partial pressure, or you can put total pressure, and the ratio will be the same. The ratio will be the same. However, here's the big however. However, if you are mixing, what does that mean? You have some substance 1 coming in and substance 2 coming in, and they're coming out of here as substance 1 plus 2. So you have nitrogen and oxygen coming in, and they're coming out as a mixture of nitrogen and oxygen. Now what happens here is you're going to have to say, when you're doing pressure Pi2 over Pi1, this one is going to be the partial pressure. And this one is just going to be the pressure. Okay, because why? At state 1, you are 100% of the mixture. So the mole fraction is 100%. So the pressure here, can be rewritten as Yi pressure 2 all over pressure 1. It's just the pressure at state 1 because you only have one substance in there. Now when we come to 2, and I should say here, maybe I should call this state here, maybe we should call this state 3. Okay, I'm going to call this combined state 3. Now when it's mixed together in 1 and 2, now you're part of the mixture. You're part of it, so you have to look at the partial pressure. Okay, you have to look at the partial pressure at that state 3. And same thing you would say that you would have Pi3 over Pi2 if we're looking at this state 2. And that would equal Yi-P3 all over P2, because in state 2, you were 100% of that mixture. But then when you mixed, it changed. And this drives people nuts. This drives people nuts, okay? If I had 1 bar of nitrogen, and I had 1 bar of oxygen, and I come out and I have 1 bar of mixture, okay? 1 bar of nitrogen, 1 bar of oxygen coming in and creating 1 bar of mixture. What's going to happen is that the nitrogen is going to decrease its partial pressure when it comes to the mixture, and the oxygen is going to decrease the partial pressure of the mixture because we're following that Dalton model. Okay, that is important for you to understand. It's not that we have 1 bar of nitrogen at state 1 and 1 bar of nitrogen at state 3. We don't. It seems like, why isn't that the case? It's because we deal with the Dalton model. And it's very important. And it can really mess up your equations if you don't think about it. Okay? So I'm going to emphasize this point. I'm going to talk to you about it again. I'm going to make sure you see it, because you will in many problems. This is super important. The partial pressures, how you deal with them. That's why I put this star on it. That's why I wanted to make sure we talked about this, okay? Please make sure you understand this lecture segment, because it can really, really mess up some problems if you don't understand. Okay.